Okay, so today is, can you all see properly?
Yeah.
Okay, so I'm going to give you an example on Coulomb's law to work on again. And so before we do that, I'll just remind you again about Coulomb's law. So we know that Coulomb's law explains the force between two charges or between charges. Doesn't have to be two, there could be multiple charges. But let's say Coulomb's law explains the force between charges, and we said that suppose you have two charges, Q1 and Q2, this is Q2, and if they are separated by distance R, then we can say that the force between the charges, so we can put the two charges there, this is Q1, let's do it this way. So we have a charge, let's call this Q1, charge Q2, and suppose they are positive charges and they repel each other, of course. So this is the force of 2 on 1, this is the force of 1 on 2. The distance between them, let's say, is R. So Coulomb's law says that the force of 1 on 2 is equal to force of 2 on 1, which is equal to the force between the charges. And that is given by K Q1 Q2 over R squared. And let's use the magnitude of the charge. Last time I did it without a magnitude, so let's do it with a magnitude so that we shall not worry about the sign of the charge. When you do it with the sign of the charge, it only tells you that if the sign of the force is negative, the two charges attract each other. If the sign is positive, they repel. But the sign of the force itself doesn't represent the direction of the force. It's just telling us whether they are attracting or repelling. So we shall use the magnitude of the charge when we are doing the calculation, and let a vector direction come out when we draw forces between different charges. So basically, we did this last time, and so let me give you an example that you can try. So we shall find the force on charge Q3. I'll put this on a Cartesian coordinate system like that. So we have one charge here, one charge here, and one charge there. So we shall have Q1, Q2, and Q3. Q1, let's say Q1 is a charge 5 microcoulombs. Q2, let's put Q2, it's -2. And Q3 is also 5 microcoulombs. Okay, so these are both positive charges. So this is a positive charge, and a negative charge. And then the distances, let's say this is A. So they are located at the corners of a right triangle as shown here. This is A. This distance is also A. So A is equal to 0.1. So the question is to find the force on charge Q3. So see if you can do this exercise, finding the force on charge Q3. So the first thing, let me start you off so that we can get it going. The first thing is to know that Q1 and Q3 repel. And so if you can think of it that way, then you can say that this is the force between 1 and 3. And Q2 and Q3 attract, so the force between 2 and 3 is going to be that way. Okay, so I've gotten you started on the two forces involved. So this is force between 2 and 3. Okay, so now you can find the force on charge 3 due to the two charges, charge 1 and charge 2. So work on that and let's see what you get. Okay, so let me give you an additional hint so that we can move it along. So you can imagine that you have charge 3 here, Q3, and you have F13 and F23. So if you think of this as the coordinate system, this is your x-axis and this is your y-axis, then you have a component F13x, and then you're going to have a component F13y. And this f23 is just the same as f23x because it's already along the x-axis. So what we need to do is to find the f13 first, and then we shall find the f13 along the x, f13 along y, and then f23 along x. So you need to know some angle here. Whatever that angle is, you can call it theta. So you need to figure out what theta is.
60.
What? No, 45. Very good. So it looks like 45. A lot of you have got it. So the angle theta can be found by taking the trigonometry of by taking the geometry that I've given you. So if you have this geometry the way it's given to you, this is A and that's A, then you can find an angle here, theta, if you like, by saying that tangent theta is equal to A over A, or you can say theta is the tangent inverse of 1, which is equal to 45 degrees. So your angle is 45 degrees. Okay, so now you can do the rest of the work. So let's see how far you go. Because it's 45 degrees, then that is also theta. So this gives you an idea on how to progress, or at least how to proceed. Which one do you have? F1?
F.
Oh, F net?
Yes.
What do you have as an answer? 7.93 newtons. Okay, so we have an F net which is 7.93. What is your direction for the magnitude, for the force? Do you have a phi that we can use? Let me go to the next page. Okay, so at least what I want you, where I want you to be is you have this F13, and you have this component F13x, F13y, and then you have F23 here, and this is just F23x. Okay, so your net force on the charge 3, net force on 3 is equal to the force of 1 on 3 plus the force of 2 on 3. Okay, and we just have to split it up into the x component. So we can say that in the x direction, the net force in the x direction is equal to the force of 1 on 3 in the x direction plus force of 2 on 3 in the x direction. And then in the y direction, you say the net force on 3 in the y direction is the force of 1 on 3 in the y direction plus the force of 2 on 3 in the y direction. Okay, and we know that the force of 2 on 3 in the y direction is equal to 0 because there is no components there. Okay, so we need to find the force of 1 on 3 in the x direction, this component here. This is theta, of course, this component here, F13x. So F13x is what?
7.95.
Okay, that's what Shahab is also getting, 7.93. That's pretty close.
Wait, the x version?
Well, you gave me net, right? Are you giving me x?
Yes.
Okay.
Now give me your x.
The x component?
Yeah.
Okay. I don't know what it is now, so let's do it together. So F13x is equal to F13 cosine 45 because we know the angle is 45 degrees, and F13y is equal to F13 sine 45, and then F23x is just equal to F23. So all we need to do is to find F13 and F23, and then we take the cosine 45 of the F13, take cosine 45, sine 45 of F13 to get F13x and F13y, and then we'll do the same for F23x. F23x is just the magnitude of F23, whatever it is. Okay, so what is F13? Okay, so it's K, Q1, Q3, if you use the magnitudes, divided by the distance between 1 and 3. That is, what is the distance between 1 and 3?
0.14. Yeah.
Okay, so 0.14 squared. So basically, if you look at the geometry, this is A, that's A. So this is going to be the square root, this is A plus A, square root of A squared plus A squared. So it's just the square root of A, isn't it? Hold on a second. So this is just by Pythagoras Theorem. So we shall say by Pythagoras Theorem, this distance here is equal to A squared plus A squared, which is equal to 2A squared. So it's equal to A root 2. So A root 2 is 0.141. So from here, what did you get for F13? What was the answer for F13? Just this itself.
4.59.
What did you get?
4.59.
Is everybody getting 4.59 for F13?
No.
What do you have?
I got 11.47.
Okay, I think 11.4 is fine. Yeah. And then what about F23? So F23 is equal to K Q2 Q3 divided by A squared. Take the magnitude of the charges. Okay. So what do you have for F23? 8.99 newtons. Okay. So now we can say that F13x is equal to 11 cosine 45, which is equal to what?
8.1.
8.1. Cosine 45 is 0.7071, I think, right? And then F13y is equal to 11 sine 45, which is 11 times 0.7071. So that should also be 8.1 newtons. So we've got the F13x, F13y. So the net force along x is equal to the square root of, no, sorry, not square root. What is that? Yeah. So, yeah, so we have F13x. So now we've done the forces, but look at the directions here. So F23x is negative, F13x is positive. So we're going to take the F13x and subtract F23x from it. Okay. So this minus F23x. So it's going to be, one of them is, this one is F13x is 8.9, sorry, 8.1 minus 9, right? So what does that give you? Minus what? 0.9 newtons. And then F net y is equal to the component in the y direction, which is just 8.1 newtons, right? You all see that?
Yeah.
Yeah. So we can say now that we've got the net force. So the net force is equal to the square root of the x component squared plus the y component squared, which is the square root of the x component is negative 0.9 squared plus 8.1 squared. So that gives us the net force, whatever that happens to be. What do you have for that?
8.05.
Okay, so it's about 8 newtons. So 7.95 or 7.93 for net is fine, if you got that. And then we have the direction. So to get a direction, we take the direction to be phi, and this will be the tangent inverse of the y component divided by the x component. So the y component is, so let's say f and y over f and x like that. So the direction is tangent inverse of y. What is the y? 8.1 over 0.9. What does that give us? What?
8365.
So the direction is 83.7 degrees. Is that what you're getting? What did you have?
We have to put minus.
No, when you are doing the direction, you don't need to use just the magnitude. Yeah, you don't need the direction, the sign. So you said 83 degrees. And then let's write it also in the Cartesian in the coordinate vector notation or unit vector notation. So we said we had a net force F net on the charge, which was given by the x component, which is negative 0.9, and the y component was 8.1. And so in unit vector notation, you can write negative 0.9 I hat plus 8.1 j hat like that. Let me just erase this and rewrite it. So 8.1 j hat. So this is the unit vector notation. Any questions at this point? Okay, so let me give you an idea how this looks like. So basically, we had the charge 3 at this point, and we had one charge. This is F13. Sorry, F13. Let's make sure we get that. F13. And then we had an F23 this way. If we look at the magnitudes, F23 was, what was F23? F23 is basically 8.99, and F13, so F23 is 8.99, that is along the x, and the net F13 was negative 0.9. So let's take a look. The x component, negative 0.9. So basically, this is what we had. Let me redraw this for you. So net force 2,3, and we say 2,3 was 9. Let me see if I can draw it to scale. So let's say this is 9, F23, and then the F13, the net F13, you said was what? A negative point. The x component is negative 0.1, so something like that. Is that in the right direction? Let me see. 13x, 23x. Okay. So this is the charge 3, and so the x component is negative 0.9. The y component is 9, something like that. So this is 8.99. So if you think of it, your direction is going to be like that. So this is basically what we have. So this is our angle, 83 degrees, 83.65, I think it was. And this is your net force. You all see that? So the y component is the tall one there, 8.1 actually, not 8.9, 8.1. And the x component is negative 0.9. So the x component is very short. That explains why we have an angle of 90 degrees as our magnitude. You all see that? So again, this is what it looks like. So you had a force like that and a force like that. And so if you think of it that way, this x component is very short. And so what that leads to is something that gives you, let me see if I can draw this to scale. This is 45 degrees. Let's see, that's too high. That's not 45. Something like that, maybe 45 degrees. Something like this. So that gives you, if you like to draw it, something that will look like that. So your angle should be something here. This is your net force. Okay, so it should be in line with this one. So these two should be the same, as you can see there. It should be something like that. So this is the direction that we are talking about. This direction is about 83 degrees, which is what this is.